More than 4 billion miles from Earth, beyond the orbit of Neptune, the solar system begins to fill with worlds that were never supposed to remain unfinished. For centuries, astronomers believed this region was almost empty. They were wrong. In 1992, an entire frontier of the solar system emerged from the darkness. Not a single forgotten planet, but a vast belt containing countless frozen worlds, each preserving a chapter from the earliest days of planetary formation. Humanity has visited this place only once. The New Horizons spacecraft left Earth at the fastest speed ever achieved by a mission to another planet, yet it still needed 9.5 years just to reach the belt's inner frontier. Far beyond Pluto, it encountered the most distant world ever explored. Instead of finding a battered relic, scientists discovered an object so perfectly preserved that it appeared almost untouched since the solar system was born. That single encounter challenged long standing ideas about how planets begin. It also raised a more unsettling question. If this distant region contains so many ancient worlds, why did none of them become planets? What stopped their growth while worlds like Earth continued to evolve? And why do the strange paths of some of these frozen bodies hint that something enormous may still be hiding even farther from the sun? The edge of our solar system is not a frozen wasteland. It is a graveyard of worlds that almost became something more. We make these long form space documentaries because we love this stuff, and so do you. If you want to keep exploring with us, subscribe and we'll be here whenever you need a quiet journey through the cosmos. Now, let's begin. To understand the frozen worlds beyond Neptune, we first need to picture the solar system before any planet existed, long before mountains, oceans, or even sunlight reflected from finished worlds. Everything around our young sun belonged to a single structure called the protoplanetary disk. This was a broad, flattened cloud of gas and dust, turning slowly through space while gravity gathered tiny grains into larger clumps over immense stretches of time. Within that disk, distance shaped destiny. Astronomers measure those distances using the astronomical unit. One astronomical unit equals 93 million miles, the average distance between Earth and the Sun. From this point forward, it becomes the simplest way for us to follow how conditions changed as we move farther from the center. Close to the Sun, inside roughly 5 astronomical units, the disk remained warm and densely packed with material. Countless collisions happened every day across that crowded region. Dust became pebbles, pebbles became boulders, boulders merged into growing worlds. Each successful collision created stronger gravity, attracting even more material until Mercury, Venus, Earth, and Mars gradually emerged from the surrounding cloud. Farther outward, between about 5 and 30 astronomical units, temperatures dropped enough for water, ammonia, and methane to freeze onto rocky particles. Ice may seem fragile to us, yet in this environment it dramatically increased the amount of solid building material available. Growing worlds accumulated mass much faster. Jupiter and Saturn formed enormous solid cores that became powerful enough to pull vast envelopes of hydrogen and helium from the surrounding disk, transforming them into giant planets. Beyond 30 astronomical units, the story unfolded very differently. The protoplanetary disk stretched across an enormous volume, leaving its ingredients scattered across tremendous distances. Each object traveled around the Sun on an orbit lasting hundreds of years. Encounters became uncommon. When two bodies finally crossed paths, another opportunity might not arrive for countless generations. The essential ingredients remained present. Rock drifted beside frozen water, methane, ammonia, and primitive organic compounds. Nothing important was missing from the recipe itself. What disappeared was opportunity. There simply were not enough frequent encounters for small bodies to merge into steadily larger ones before the remaining gas and dust dispersed from the young solar system. Time became another invisible limit. Planet formation is a race against a changing environment because the material surrounding a newborn star does not remain forever. As the disk gradually cleared, the supply that growing worlds depended upon faded away. Many distant objects were left suspended between beginnings and completion, carrying the chemistry of planets without ever reaching planetary size. When we look beyond Neptune today, we are not seeing shattered worlds whose histories ended in catastrophe. We are seeing countless planetary candidates preserved before their stories truly began. Their existence traces back to one decisive chapter in the solar system's earliest history, when the path toward full planetary growth changed forever. Among all the worlds that emerged from the young solar system, one changed the fate of every object beyond Neptune more than any other. Jupiter did not simply become the largest planet. Its astonishing growth altered the balance of the entire protoplanetary disk, reaching far beyond its own orbit through the invisible pull of gravity. Jupiter formed with remarkable speed because it occupied a region rich in both rocky material and frozen ice. Those combined ingredients allowed a massive solid core to assemble far earlier than anywhere else. Once that core reached a critical size, gravity began drawing in surrounding hydrogen and helium at an accelerating pace. In a comparatively brief span of cosmic history, Jupiter transformed from a growing planetary embryo into a giant whose influence extended across much of the newborn solar system. As its mass increased, the surrounding disk no longer drifted in the same orderly way. Gravitational disturbances spread outward, changing the motions of countless distant bodies. Paths that had once crossed gently became increasingly energetic. Objects approached one another at much greater speeds, and the consequences changed completely. Planetary scientists call the process of bodies sticking together through repeated impacts accretion. In simple terms, accretion is growth by collision. Within the inner solar system, many impacts happen slowly enough for rock to merge rather than break apart. Every successful collision produced a larger object with stronger gravity, making future growth even more likely. Far beyond Jupiter, the story shifted. Higher impact speeds turned many encounters into destructive events, scattering fragments instead of creating larger worlds. This marks the first part of our answer. Jupiter weakened the outer disk's ability to build planets, yet gravity alone does not explain everything we find beyond Neptune today. Another boundary shaped the young solar system from the beginning. Astronomers call it the frost line, the distance from the sun beyond which water, ammonia, and methane could remain frozen instead of evaporating. It lay around 3 astronomical units from the sun. Beyond that boundary, icy material became as important as rock when building planetary bodies, giving distant objects very different internal compositions and changing how they responded during collisions. Even without Jupiter's growing influence, the farthest reaches of the disk faced another challenge. Beyond 30 astronomical units, each orbit around the Sun required roughly 200 to 300 years. Bodies remained separated by immense distances, meeting only after extraordinarily long intervals. Imagine waiting centuries for a single opportunity to grow, only for that encounter to end in fragmentation instead of union. The mathematics alone placed severe limits on planetary construction. We can now see two overlapping obstacles working together. The outer disk held too little material across too much space, while Jupiter continuously stirred that fragile environment into greater disorder. Growth slowed, then stalled, leaving behind countless icy bodies suspended between possibility and completion. Those survivors remained in their distant paths, preserving a chapter of the solar system that the larger planets had already left behind. For generations, the map of the solar system appeared complete. Textbooks ended with Neptune, and beyond its orbit stretched what astronomers believed was an almost empty frontier. This was more than a convenient simplification. It was the accepted picture of our planetary neighborhood, repeated across classrooms, observatories, and scientific papers throughout most of the 20th century. One astronomer suspected the story might reach farther. In 1951, Gerard Kuiper proposed that short period comets, those returning to the inner solar system in less than 200 years, likely originated from a broad disk beyond Neptune. Yet even Kuiper believed that ancient gravitational disturbances had swept this region clean long ago. If such a disk had ever existed, he thought its original residents had already disappeared. Several decades passed with little reason to challenge that conclusion. Then, in 1987, David Jewett at the University of Hawaii began an ambitious search with his graduate student, Jane Liu. Using the university's telescope atop Mauna Kea, they committed themselves to an unusually patient survey. Rather than chasing spectacular discoveries, they repeatedly photographed the same regions of sky, searching for an object that shifted ever so slightly against the fixed background of distant stars. The work demanded remarkable persistence. Night after night, year after year, the images revealed nothing unexpected. 5 years passed without success. Jewett later admitted that he had begun wondering whether the search itself rested on a mistaken idea. Imagine spending years looking where nearly everyone expected emptiness, while each observation seemed to confirm that expectation. Then, on August 30th, 1992, persistence finally met evidence. A faint point of light moved just enough between observations to distinguish itself from the surrounding stars. The object received the designation 1992 Quebec Bravo 1. It orbited at approximately 41 astronomical units from the Sun and measured roughly 160 miles across. Its location matched the predicted region beyond Neptune, where almost nobody expected substantial bodies to remain. Jewett and Liu immediately recognized they had uncovered something far more significant than another comet or wandering asteroid. They had identified the first confirmed member of an entirely new population of solar system objects. Once astronomers knew where and how to search, additional discoveries followed within months. The apparent emptiness beyond Neptune began filling with distant worlds. During the following decade, the known population expanded from one object into hundreds. Each new discovery strengthened the conclusion that the outer solar system contained a vast belt of ancient bodies waiting to be cataloged. Planetary science adapted rapidly, rewriting long accepted models to include a region that had remained hidden in plain sight. The name that endured was the Kuiper Belt, even though Gerard Kuiper's original picture proved incomplete. There is something deeply human in that outcome. Science often honors those who ask the right questions, even when later generations uncover different answers. We move forward together, one careful observation at a time, allowing evidence to reshape even our most established maps of the cosmos. Long before we measure orbits or classify distant worlds, it helps to look more closely at the material from which they are built. Composition tells a story that motion alone cannot. Every frozen surface beyond Neptune preserves clues from the earliest chapter of the solar system, waiting for us to read them with modern instruments. Most Kuiper Belt objects consist primarily of frozen volatile materials, substances that easily become gas closer to the sun but remain solid in the deep cold of the outer solar system. Water ice forms much of their structure, joined by methane and ammonia, locked into place at average surface temperatures near 400 degrees below zero Fahrenheit. Mixed throughout are silicate rock and dark carbon-rich material that has remained largely unchanged since the protoplanetary disk first condensed more than 4.5 billion years ago. Their colors reveal another remarkable process. Many of these distant worlds display rich reddish-brown surfaces rather than brilliant white ice. The change comes from cosmic radiation, streams of energetic particles arriving from both the sun and deep space. Over immense spans of time, those particles strike frozen methane and gradually break apart its molecules. The liberated carbon atoms recombine into increasingly complex substances called tholins. Tholins are radiation-cooked carbon compounds that slowly accumulate into a dark reddish crust on icy worlds exposed to space for vast ages. You may already have encountered this chemistry without realizing it. Similar tholins contribute to the reddish coloring near Pluto's north polar region. They also help produce the thick orange haze surrounding Saturn's moon Titan, and instruments aboard the National Aeronautics and Space Administration spacecraft New Horizons detected them across the surface of Arrokoth. The same chemical fingerprints appear again and again, connecting worlds separated by extraordinary distances. Astronomers have learned to treat color as more than appearance. By measuring how red and dark a surface has become, they can estimate how long it has remained exposed to cosmic radiation without being resurfaced by impacts or geological activity. A fresher surface often appears brighter, while older terrain gradually deepens into darker shades after countless ages beneath the steady rain of energetic particles. The ice itself behaves unlike anything we experience on Earth. At 400 degrees below zero Fahrenheit, water ice becomes extraordinarily rigid, with mechanical strength exceeding that of many common rocks. If you could stand upon one of these distant bodies, the frozen ground beneath your feet would respond more like granite than the brittle ice found on a winter lake. Yet, a few of these objects may still possess hidden activity. Spectroscopic evidence, meaning light analyzed into its individual wavelengths to reveal chemical composition, suggests that some contain cryovolcanism. Instead of molten rock erupting from below, cryovolcanoes release slushy mixtures of water and ammonia driven upward by lingering internal heat. These eruptions reshape icy landscapes while remaining unimaginably cold. We are therefore looking at far more than frozen debris. Each object preserves ancient chemistry, records billions of years of radiation, and in rare cases still reshapes itself from within. They remain among the oldest surviving materials in the solar system, carrying their original ingredients across time with remarkable fidelity. Few worlds have occupied such a remarkable place in our imagination as Pluto. When astronomer Clyde Tombaugh discovered it in 1930 at the Lowell Observatory, the announcement completed what generations believed was the family of planets. For the next 76 years, Pluto held the title of the ninth planet with remarkably little disagreement. If you opened a textbook, visited a planetarium, or memorized the planets at school, Pluto always appeared at the end of the list. The facts describing Pluto seemed straightforward. It circles the Sun at an average distance of 39 astronomical units and requires 248 Earth years to complete a single orbit. Measuring 1,473 miles across, it is smaller than Earth's own moon, which spans 2,159 miles. Those numbers were well established long before anyone questioned what Pluto should be called. What changed was the broader picture surrounding it. As astronomers continued discovering more distant objects throughout the 1990s and early years of the new century, Pluto gradually lost its appearance of uniqueness. World after world emerged from the outer solar system, sharing similar sizes, compositions, and distant orbits. Instead of standing alone beyond Neptune, Pluto became the largest familiar member of an expanding population. This growing census forced astronomers to confront an unexpectedly difficult question: what exactly is a planet? Until then, science had never adopted a formal definition because there had never been much need. In 2006, the International Astronomical Union gathered to establish one. Their final definition required that a planet satisfy three conditions. It must orbit the Sunday. It must possess enough gravity to pull itself into a nearly spherical shape. Finally, it must clear its orbital neighborhood, meaning its gravity has become overwhelmingly dominant within its path around the Sunday. Pluto satisfies the first two requirements with ease. The third proved decisive. Rather than dominating its orbital region, Pluto shares that distant realm with thousands of neighboring Kuiper Belt objects. Under the newly adopted definition, it entered a different category, becoming a dwarf planet instead. The response extended far beyond astronomy. Newspapers filled with editorials, petitions circulated. Teachers, students, and lifelong skywatchers debated the decision with surprising passion. Many people felt that an old companion had somehow been diminished. Yet if you step back and look with fresh eyes, the opposite had happened. The solar system had become richer. Instead of one lonely planet beyond Neptune, we discovered an entire community of ancient worlds stretching across the outer reaches of the Sun's domain. Pluto had not become less interesting. It had gained thousands of companions. Its own family is remarkable as well. Pluto possesses 5 known moons. Charon, measuring 751 miles across, is so large relative to Pluto that both bodies orbit a shared center of gravity located between them rather than inside Pluto itself. Alongside Charon travel Styx, Nix, Kerberos, and Hydra, completing one of the most unusual planetary systems known before humanity finally viewed Pluto as more than a distant point of light. A spacecraft left Earth carrying answers to questions that had not yet been asked. On January 19, 2006, the National Aeronautics and Space Administration launched New Horizons toward Pluto. Later that same year, astronomers voted to redefine Pluto as a dwarf planet. By then, the mission destined to transform our understanding of that distant world was already racing outward, committed to a journey that could not be recalled. New Horizons departed faster than any spacecraft before it, accelerating to roughly 36,000 miles per hour only hours after launch. At that speed, you could travel from New York to Los Angeles in less than 5 minutes. Even so, the voyage to Pluto demanded extraordinary patience. The spacecraft crossed the vastness of the outer solar system for 9 years and 5 months before finally arriving on July 14th, 2015. Distances beyond the giant planets resist ordinary intuition, revealing themselves only through years of uninterrupted travel. The spacecraft itself remained surprisingly compact. New Horizons weighed only 1,054 pounds and carried 9 scientific instruments inside a body roughly the size of a grand piano. Every unnecessary ounce had been removed before launch, so more fuel could be reserved for tiny course corrections during its 3 billion-mile journey. Those carefully planned adjustments ensured the spacecraft would cross an invisible target window only a few dozen miles wide, after traveling farther than any previous planetary mission of its kind. Arrival brought another challenge. New Horizons could not slow down and enter orbit, because doing so would have required far more fuel than any practical launch vehicle could carry. Instead, it performed a single flyby lasting about 22 hours while moving at approximately 30,000 miles per hour. During that brief encounter, every camera and instrument had to work flawlessly. There would never be another opportunity to capture the same moment. Mission controllers experienced the encounter from an unusual perspective. Radio signals, crossing 3 billion miles, still required 4 hours and 25 minutes to reach Earth, even while traveling at the speed of light. By the time engineers received confirmation that each observation had succeeded, the spacecraft had already completed those operations long before. What New Horizons revealed overturned decades of expectation. Pluto emerged as a geologically diverse world rather than a frozen relic. Towering mountains of water ice rose nearly 11,000 feet above the surrounding plains. A vast heart-shaped basin, later named Tombaugh Regio, displayed flowing nitrogen ice organized into immense convection cells, circulating slowly as warmer material rose and cooler material sank. These patterns pointed toward lingering internal heat inside a world that many models had predicted should have become geologically inactive billions of years earlier. Every image expanded the meaning of what a small, icy world could be. Instead of finding an ending, we discovered complexity waiting at the edge of the known solar system. With fuel and electrical power still available, New Horizons continued beyond Pluto, carrying humanity farther into the Kuiper Belt than any spacecraft had ever traveled before. On the first day of 2019, New Horizons reached another destination few people had even heard of before the mission began. 4,100,000,000 miles from Earth, the spacecraft swept past a tiny frozen body, originally designated 2014 Mike Uniform 69. It later received the name Arrokoth, a Powhatan word meaning sky. With that encounter, humanity explored the most distant object ever visited by a spacecraft, extending our reach more than 1 billion miles beyond Pluto. At first glance, Arrokoth seemed almost modest. It lacked towering mountains, broad plains, or a visible atmosphere. Yet the closer images arrived, the more extraordinary it became. Rather than appearing as a single rounded world, Arrokoth consisted of two separate lobes joined together by a narrow neck. Before its official name was adopted, mission scientists informally called those lobes Ultima and Thule. One measures about 12 miles across, while the other spans roughly 9 miles. Together they form what astronomers describe as a contact binary, two independent bodies resting against one another after an exceptionally gentle merger. That gentle contact became the greatest surprise. Evidence indicates both lobes formed within the first million years of the solar system, while orbiting each other inside the same local cloud of the protoplanetary disk. Their relative speed was astonishingly low, only about 1 to 2 miles per hour, comparable to the pace of a relaxed walk. They drifted together so delicately that neither body fractured, deformed, nor displayed the scars expected from a violent collision. They simply touched and remained together. Its surface preserved another remarkable clue. Large impact craters are almost entirely absent. Across 4,560,000,000 years, nothing substantial appears to have struck Arrokoth. That pristine condition confirms it has remained within the cold classical region of the Kuiper Belt since the solar system was less than 1 million years old, escaping the disruptions experienced by many neighboring populations. For decades, many planetary scientists favored a model in which countless small bodies formed through energetic, chaotic collisions inside a turbulent disk. Arakoth challenged that picture. Its undisturbed shape could not easily survive the repeated high speed impacts predicted by those earlier ideas. Instead, the observations strongly supported a different explanation known as streaming instability. This process describes tiny particles gathering into dense local concentrations, where gravity gradually pulls entire clouds inward until paired bodies naturally emerge and slowly spiral together. That conclusion reaches far beyond one distant object. If Arakoth formed through streaming instability, then the earliest building blocks of planets may have assembled through organized local collapse rather than endless destructive collisions. The architecture of our solar system begins to look less chaotic and more carefully structured than astronomers once imagined. Even today, sunlight reaching Arakoth is about 1,900 times fainter than the light bathing Earth. Across that remote frontier, this small world has remained essentially unchanged since an age preceding Earth's oceans. We are not merely observing another icy object. We are looking directly at one of the oldest surviving records of how planets first began to take shape. Some discoveries answer long standing questions, others create entirely new ones. When astronomer Mike Brown and his team at the California Institute of Technology identified a faint, distant object in November of 2003, they realized they were looking at something that fit neither expectation nor existing theory. The object received the name Sedna after the Inuit goddess of the sea, and almost immediately it challenged the accepted picture of the outer solar system. Sedna measures roughly 620 miles across, placing it among the larger icy bodies beyond Neptune. Its orbit, however, is what makes it extraordinary. At its closest approach, it comes no nearer than 84 astronomical units from the Sunday. At its most distant point, it travels out to approximately 937 astronomical units. One complete journey requires about 11,400 Earth years. Human civilization has not existed long enough to witness a full Sedna year. Distance alone is not the real mystery. We have already encountered worlds occupying remote regions of the solar system. The difficulty lies in explaining how Sedna reached such an unusual path. Every established model of the outer solar system struggles with the same obstacle. Neptune is the primary architect of the Kuiper Belt. Across billions of years, its gravity has captured, scattered, and organized countless icy bodies into the patterns astronomers observe today. Yet Neptune's effective influence fades beyond roughly 50 astronomical units. Sedna never comes anywhere near that boundary. Even at its closest approach, it remains about 34 astronomical units beyond the region where Neptune could realistically reshape its orbit through repeated encounters. Something else must have acted upon it. The search for that missing influence has occupied planetary scientists ever since. One possibility is the existence of a massive, undiscovered planet orbiting far beyond Neptune, exerting a slow but persistent gravitational pull over immense stretches of time. Another proposes that during the Sun's youth, while it still formed within a crowded cluster of neighboring stars, one passing star drifted close enough to disturb the outer disk and fling objects like Sedna onto elongated paths. A third hypothesis suggests an even stranger origin, that Sedna formed around another young star before being captured by the Sun during those early stellar encounters. For years, Sedna stood alone as an unsettling exception. Then, in 2012, astronomers discovered another distant object with a remarkably similar orbit. Officially designated 2012 Victor Papa 113 and informally nicknamed Biden, it occupies another trajectory that known planets cannot adequately explain. Independent oddities can sometimes be dismissed. Repeated patterns demand closer attention. When you place these distant worlds together, coincidence becomes increasingly difficult to accept as the complete explanation. Their orbits appear to preserve evidence of an influence still missing from our maps of the solar system. Whether that influence proves to be an unseen planet, an ancient stellar encounter, or something entirely unexpected, Sedna and Biden remain among the strongest clues that the outermost reaches of our cosmic neighborhood still hold a profound secret. By the middle of the last decade, scattered clues from the outer solar system had begun pointing toward a single possibility. In January of 2016, Mike Brown, the astronomer often associated with Pluto's reclassification, joined planetary scientist Konstantin Batygin in publishing a study that quickly became one of the most debated papers in modern astronomy. Their proposal was strikingly simple. A massive planet, still unseen, might be orbiting far beyond Neptune. According to their calculations, this hidden world could contain between 5 and 10 times the mass of Earth, while traveling at a distance of roughly 400 to 800 astronomical units from the Sun. At such distances, one orbit would require somewhere between 10,000 and 20,000 Earth years. During an ordinary human lifetime, its motion against the background stars would be so gradual that it would appear almost motionless. The argument did not begin with direct observation. Instead, it relied on gravitational fingerprints, subtle patterns left behind by an unseen object's influence. Brown and Batygin examined several distant Kuiper Belt objects, including Sedna and the object informally known as Biden. Their elongated orbits displayed an unexpected similarity. They clustered in nearly the same direction, shared comparable tilts, and pointed toward the same general region of the sky. Statistics suggested this arrangement deserved careful attention. The estimated probability of those orbital alignments occurring purely by chance was roughly 1 in 14,000. Such odds do not prove the existence of another planet, yet they are difficult to dismiss as random coincidence alone. Gravity has a habit of revealing hidden masses long before telescopes actually detect them. Finding such a world presents an enormous challenge. Even if Planet 9 exists, it would receive only a tiny fraction of the sunlight reaching Neptune. Astronomers estimate it could appear roughly 1,000 times fainter than Neptune itself, placing it below the practical detection limit of many existing telescopes. Searching for it resembles looking for a dim moving ember across an immense celestial landscape, while that ember shifts only slightly over decades. Modern observatories have accepted that challenge. The Vera Rubin Observatory, which began full survey operations during 2025, repeatedly scans the sky with extraordinary sensitivity. Its wide field observations were designed to detect faint moving objects, making the search for Planet 9 one of its most anticipated scientific goals. Yet, the opposing viewpoint remains important. Several astronomers argue that the orbital clustering may result from selection bias, meaning observers have repeatedly searched the same portions of the sky, while other equally distant regions remain less explored. If discoveries naturally accumulate where telescopes spend the most time looking, apparent patterns may emerge without requiring an unseen planet at all. As of 2025, neither interpretation has prevailed. Planet 9 remains unconfirmed, yet it has not been ruled out. If it ultimately exists, a single distant world could explain Sedna, Biden, the clustered Kuiper Belt orbits, and several other lingering puzzles at once. If it does not, astronomers will need to rethink how they interpret the farthest reaches of our solar system, refining the maps of a frontier that continues to surprise us. Numbers become strangely abstract once they grow large enough. We can recite them with ease, yet our minds rarely transform them into places we can genuinely picture. To understand the Kuiper Belt, we have to pause for a moment and let its scale settle into something more tangible. Because this distant population occupies a realm unlike anything else in our planetary neighborhood. The Kuiper Belt stretches from about 30 astronomical units to roughly 50 astronomical units from the Sunday that forms a band, approximately 1,860,000,000 miles wide. Even after everything we have explored so far, it remains difficult to appreciate what that span truly represents. We are not looking at a narrow ring surrounding Neptune. We are looking at an enormous frontier extending across distances that exceed the width of many entire planetary systems discovered around other stars. Within that vast region, astronomers estimate at least 100,000 objects measure more than 60 miles across. That figure is deliberately conservative because current telescopes can reliably detect only the brighter and larger members of the population at such extreme distances. Beneath that visible layer lies another reality. When smaller bodies are included, the total population likely reaches into the trillions. Despite those astonishing numbers, the belt itself is remarkably diffuse. Its combined mass is estimated to equal roughly 25 to 30 Earths, yet all of that material is spread through an immense volume of space. Imagine scattering that much matter across a region so expansive that neighboring worlds large enough to see are commonly separated by millions of miles. The result bears little resemblance to the crowded fields, often portrayed in motion pictures. If you could somehow stand aboard a spacecraft drifting through the middle of the Kuiper Belt, you would probably see nothing nearby. Hours could pass without another substantial object appearing outside your window. The emptiness would dominate your surroundings far more than the countless frozen bodies sharing the same distant realm. Space, even inside a populated region, remains overwhelmingly spacious. The asteroid belt between Mars and Jupiter offers a useful comparison. Popular culture frequently imagines it as a dangerous maze, demanding constant evasive maneuvers. Real spacecraft cross that region routinely because the actual separation between asteroids is immense. The Kuiper Belt is even more spread out relative to its total volume, making accidental encounters extraordinarily unlikely. Among the known residents, Pluto remains the largest confirmed member at 1,473 miles across. Yet astronomers do not expect that title to remain secure forever. More distant populations, especially within the scattered disk and regions beyond, almost certainly conceal additional worlds comparable in size, perhaps even larger, awaiting discovery. The inventory we know today is only an opening chapter. The Vera Rubin Observatory is expected to increase the number of identified Kuiper Belt objects by a factor of 10 to 100 during its first decade of operations. With every new survey, this immense outer population becomes less like a handful of isolated discoveries and more like a true planetary landscape whose boundaries we are only beginning to chart. Far beyond the more orderly lanes of the main Kuiper Belt, another population begins to emerge. These worlds belong to a different family, one shaped by repeated encounters with a restless giant planet rather than long stretches of relative stability. Their paths preserve a record of disturbance, allowing you to read an ancient gravitational struggle that never truly came to an end. Astronomers call this region the scattered disk. It stretches from roughly 30 astronomical units to well beyond 100 astronomical units from the Sunday. Unlike the comparatively restrained orbits of the cold classical population, these bodies follow elongated and steeply tilted paths. During one part of an orbit, they may pass comparatively close to Neptune. Centuries later, they retreat into an immense darkness, traveling far beyond the main concentration of Kuiper Belt objects before beginning the long return. Those unusual trajectories did not arise by chance. They are the unmistakable fingerprints of close gravitational encounters with Neptune during the solar system's youth. As Neptune migrated outward through the remaining debris of the protoplanetary disk, its gravity repeatedly captured passing objects for brief encounters. Each meeting acted like a cosmic slingshot, altering speed and direction before releasing the traveler into a dramatically different orbit. The planet did not destroy these worlds. It scattered them across the outer frontier. Among the largest known members of this population is Eris, discovered by astronomer Mike Brown and his colleagues in January of 2005. Measuring about 1,445 miles across, Eris is remarkably similar in size to Pluto. Yet its average distance from the Sun is approximately 68 astronomical units, and its elongated orbit carries it as far as roughly 97 astronomical units. You can almost picture a world spending most of its existence in regions where sunlight has become unimaginably faint. Eris quickly became far more than another distant discovery. Its existence confronted astronomers with an uncomfortable question. If Pluto remained a planet, then should Eris receive the same designation? If Eris did not qualify, could Pluto honestly keep its long accepted place? Brown later reflected that discovering Eris convinced him Pluto's classification would eventually change because the two objects shared the same fundamental nature despite occupying different neighborhoods. The resulting debate led directly to the International Astronomical Union redefining the word planet in 2006. Pluto's reclassification became one consequence of a much larger realization. The outer solar system contained an entire population of substantial icy worlds, and Eris demonstrated that Pluto was one representative among many rather than a solitary exception. The scattered disk continues to influence the solar system today. Many short period comets, those completing an orbit in less than 200 years, begin their inward journeys here. Gentle but persistent gravitational nudges from Neptune gradually reshape certain orbits until these frozen bodies descend toward the inner planets. As they approach the Sun, their ancient ices transform directly into gas, producing the glowing comas and sweeping tails visible from Earth. The scattered disk, therefore, remains the outer solar system's most dynamic frontier, where Neptune's influence still redirects ancient worlds, proving that planetary evolution did not end billions of years ago but continues, one distant orbit at a time. Long before anyone mapped the distant populations beyond Neptune, one planet had already been shaping their destinies. Every broad ring, every stable family of icy worlds, and every wildly stretched orbit carries the imprint of a gravitational architect that has been at work since the earliest chapter of solar system history. To understand why the Kuiper Belt looks the way it does, we have to follow Neptune through billions of years of slow, persistent influence. Neptune circles the Sun at exactly 30 astronomical units, making it the closest giant planet to the Kuiper Belt. From that position, its gravity dominates the motions of countless distant objects. You might imagine its influence fading quickly with distance, yet over immense spans of time, even small gravitational nudges accumulate into dramatic changes. A single orbit means little. Millions of them reshape an entire region. Current models of solar system formation, especially the NICE model developed during the early 2000s, suggest Neptune was not born where we find it today. Instead, it likely formed much closer to the Sun, perhaps near 18 astronomical units. Over hundreds of millions of years, it gradually migrated outward, exchanging momentum with countless planetesimals, the small building blocks of planets, scattered throughout the young protoplanetary disk. Every encounter shifted Neptune outward by a tiny amount while sending other objects onto new paths. As Neptune advanced, it swept through the outer disk like a patient shepherd gathering a wandering flock. Some bodies escaped entirely. Others became trapped inside orbital resonances, gravitational relationships where orbital periods remain locked into exact numerical ratios. These resonances act like repeating rhythms, allowing objects and Neptune to exchange gravitational tugs without colliding. Pluto provides the most famous example. It occupies a 3-to-2 resonance with Neptune. During every two complete orbits Pluto makes around the Sun, Neptune completes exactly 3. Although Pluto's path crosses inside Neptune's orbital distance, the resonance keeps both worlds separated with remarkable precision. Whenever Pluto approaches the region where Neptune travels, Neptune is always positioned safely elsewhere along its orbit. This arrangement has remained stable for billions of years. Many other distant bodies share this same resonance. Astronomers call them Plutinos, and hundreds have already been identified. Pluto simply happens to be their largest known representative. Their existence preserves a record of Neptune's outward migration, revealing that these gravitational locks were established while the giant planet slowly changed position. Migration also transformed the outer solar system itself. Computer simulations indicate the original Kuiper Belt contained between 20 and 100 times more mass than survives today. Much of that ancient population never remained in place. Some objects were scattered into the distant, scattered disk. Others escaped the sun's gravity entirely, becoming interstellar wanderers. Still more were redirected inward, contributing to the heavy bombardment that reshaped the young planets. Neptune may even display its greatest captured prize. Its largest moon, Triton, measures roughly 1,700 miles across and travels in a retrograde orbit, moving opposite Neptune's rotation. Such an orbit is extraordinarily difficult to produce naturally around a forming planet. The simplest explanation is also the most remarkable. Triton began life as a Kuiper Belt object before Neptune captured it during a close encounter, preserving within its orbit one final reminder that this distant giant has been sculpting the solar system almost since the beginning. Long after the planets had largely taken shape, the solar system entered another defining chapter. The broad architecture was already recognizable, yet the balance had not settled. Far beyond the familiar planets, enormous reservoirs of icy and rocky bodies still waited in unstable orbits. Then, roughly 4 billion years ago, that balance shifted, and the consequences reached every solid world in the inner solar system. The evidence remains preserved across ancient landscapes. The Moon, Mercury, and Mars all display a striking concentration of enormous impact craters dating to nearly the same period. After that interval, the rate of major collisions fell dramatically. Earth almost certainly experienced the same assault, although erosion, tectonic activity, and oceans erased most of its earliest scars. Venus likely shared the experience as well, but its continually renewed surface concealed the record beneath younger volcanic plains. Our clearest archive comes from the Moon. Its ancient highlands are crowded with overlapping impact basins that formed within a comparatively narrow span of time. Samples collected by National Aeronautics and Space Administration Apollo astronauts revealed that many of the largest basins crystallized between approximately 4 billion, 100 million, and 3 billion, 900 million years. Instead of recording a steady rain of impacts, the lunar surface preserves the signature of a sudden surge, followed by a pronounced decline. The leading explanation once again points toward the NICE model. According to this picture of early solar system evolution, Jupiter and Saturn eventually entered a 2-to-1 gravitational resonance. Jupiter completed 2 orbits around the Sun during the same interval. Saturn completed 1. That repeated alignment amplified their combined gravitational influence, disturbing the outer planets and altering Neptune's orbit. What followed unfolded across hundreds of millions of years. As Neptune migrated outward through the primordial Kuiper Belt, it scattered vast numbers of planetesimals from their original paths. Some escaped into interstellar space. Others remained trapped in distant populations we have already explored. Countless more were redirected inward. Together, they formed an immense wave of icy and rocky bodies crossing the orbits of the young terrestrial planets. The bombardment was not a single catastrophic day. It was a prolonged era during which impacts became dramatically more common than before or afterward. For the young Earth, the consequences were profound. Any primitive life that might have emerged during the first few 100 million years would have faced repeated global devastation from colossal collisions. Entire oceans may have boiled locally after the largest impacts. Vast quantities of rock were blasted into the atmosphere before falling back across the surface. Conditions suitable for stable biological development were repeatedly interrupted. Yet the same incoming objects may also have carried remarkable gifts. Many originated in the cold outer reaches of the solar system, where frozen water and complex organic molecules survived from the earliest stages of planetary formation. Each collision delivered additional material to the growing Earth. Over immense spans of time, these arrivals may have contributed both water and carbon-rich compounds that later became part of the environment from which life eventually emerged. Seen from this perspective, the Kuiper Belt is far more than a distant collection of frozen worlds. It participated directly in Earth's history, sending both devastation and possibility inward, leaving our own planet shaped by events that began billions of miles away. Long before telescopes revealed where comets come from, people watched brilliant visitors cross the night sky without warning. They appeared, brightened, and disappeared again, leaving generations to wonder whether they were omens or wandering stars. Today, we know those luminous travelers begin their journeys far beyond the familiar planets, carrying with them material preserved since the birth of the solar system itself. Most comets visible from Earth trace their origins to the Kuiper Belt or the more distant, scattered disk. Short-period comets, those completing an orbit in less than 200 years, usually begin as ordinary icy bodies circling the Sun beyond Neptune. Over immense stretches of time, repeated gravitational encounters with Neptune gradually reshape their orbits. Eventually, one of those distant worlds is redirected inward, beginning a journey that transforms it from an obscure frozen object into one of the brightest sights in the sky. The change begins as the comet approaches within a few astronomical units of the sunday. Increasing warmth reaches its surface, where frozen volatile materials begin sublimating, a process in which a solid changes directly into gas without first becoming liquid. Escaping gases carry fine dust into surrounding space, creating a glowing cloud called the coma. Pressure from sunlight and the constant flow of charged particles streaming outward from the sun then push that gas and dust away, forming the long tails that can stretch for millions of miles across space. Because of this transformation, every bright comet represents far more than a passing spectacle. It becomes a messenger from the outer solar system, exposing material that has remained largely unchanged since planets were still assembling. By studying these ancient bodies, we examine ingredients that existed before Earth developed oceans, continents, or even a stable surface. One of the most important investigations came from the European Space Agency Rosetta mission. Between 2014 and 2016, Rosetta traveled alongside Comet 67P Churyumov-Gerasimenko while the Philae lander briefly touched its surface. Instruments detected glycine, a simple amino acid, together with formaldehyde, phosphorus, and more than 16 organic compounds connected to the chemistry that living systems eventually require. These discoveries strengthened the idea that some essential chemical ingredients for life were already present within primitive cometary bodies long before biology appeared on Earth. Another clue came from Comet Hartley 2. Scientists compared the ratio of deuterium to hydrogen in its water with the same ratio found in Earth's oceans. This chemical fingerprint matched remarkably well, providing some of the strongest evidence that at least part of Earth's water may have arrived aboard impacts from outer solar system objects during the planet's earliest history. A comet cannot continue this cycle forever. Every close passage around the sun strips away enormous quantities of frozen material, often hundreds of thousands of tons during a single orbit. Eventually, little volatile material remains. The once brilliant traveler fades into a dark, inactive body that still follows its ancient path but no longer displays a glowing coma or sweeping tail. The population we observe today represents only a tiny remnant of what once existed. Astronomers estimate that roughly 99% of the original comets formed in the outer disk have already been ejected from the solar system or destroyed over 4,600,000,000 years of gravitational evolution, leaving the few we still witness as enduring ambassadors from a far larger and far older frontier. Among the countless worlds beyond Neptune, one family stands apart through remarkable restraint rather than dramatic motion. While other distant bodies bear the marks of ancient gravitational encounters, these objects continue tracing paths that have changed astonishingly little since the earliest chapter of the solar system. Their value comes from what never happened to them. The cold classical Kuiper Belt objects occupy nearly circular orbits between 42 and 48 astronomical units from the Sunday. Their paths also have very low inclination, meaning they travel close to the flat plane in which most planets orbit instead of wandering far above or below it. The word cold does not describe temperature. Every object this far from the sun remains intensely frozen. Instead, cold refers to orbital energy, describing motion that has stayed orderly, stable, and only gently shaped across billions of years. Because these worlds escaped the strongest gravitational disturbances, astronomers believe their present orbits closely resemble those they followed shortly after the protoplanetary disk dispersed. Unlike neighboring populations scattered by Neptune or captured into resonances during planetary migration, These bodies avoided the repeated close encounters that dramatically altered so much of the outer solar system. As we examine them today, you are looking at one of the least altered surviving populations from the era when planets themselves were still taking shape. One statistic immediately distinguishes this population from every other region beyond Neptune. Between one quarter and nearly one third of known cold classical objects exist as binary systems, two separate bodies orbiting one another while together circling the Sunday. Such a high fraction is extraordinary. Comparable populations contain far fewer stable pairs, suggesting that many original binaries elsewhere were broken apart during violent gravitational interactions long ago. The persistence of these binary partners tells an important story. Their mutual gravity is relatively weak, making the pairs surprisingly delicate over cosmic timescales. A close encounter with a massive planet would often separate them forever. Since so many remain intact, astronomers conclude they must have formed together inside the same local concentration of dust, ice, and rock before gradually collapsing under their shared gravity. Once established, they experienced remarkably few disruptive events across 4,500,000,000 years of solar system evolution. Arakoth fits this picture with remarkable precision. Its gently joined lobes, uniform surface properties, and undisturbed orbit all reflect the characteristics expected from a cold classical object. Rather than surviving repeated collisions or dramatic migrations, it appears to have remained within this protected neighborhood while much of the surrounding solar system underwent profound change. Its preserved structure provides a direct test of modern theories describing how the earliest planet building blocks assembled. For planetary scientists, these distant objects function much like untouched historical records stored beyond the reach of later revisions. Every stable orbit, every enduring binary pair, and every preserved surface adds another page to a story written before Earth possessed oceans or an atmosphere resembling the one we know today. By studying the cold classicals, we move closer to observing the original architecture of the protoplanetary disk itself, preserved across billions of years with extraordinary fidelity. Beyond Pluto lies a gathering of worlds that refuses to fit a single pattern. Each follows its own path, carries its own history, and preserves a different chapter from the solar system's earliest age. Together, they remind us that Pluto is only the most familiar face in a much larger population, one whose diversity continues to expand with every new discovery. Eris remains Pluto's closest rival, measuring roughly 1,445 miles across. It circles the Sun at an average distance of 68 astronomical units and reaches nearly 97 astronomical units at its most distant point. Its lone known moon, Dysnomia, appears remarkably dark beside its brilliant parent world. By carefully tracking Dysnomia's orbit, astronomers calculated Eris's mass with impressive precision. Those measurements revealed something unexpected. Although Eris and Pluto are nearly identical in size, Eris contains about 27% more mass, making it the most massive known dwarf planet in the solar system. Makemake offers a different puzzle. Stretching about 890 miles across, it travels around the Sun at an average distance of roughly 45 astronomical units. Frozen nitrogen and methane can briefly form an extremely thin atmosphere whenever Makemake approaches the warmer portion of its orbit. That fragile envelope later freezes back onto the surface as the world retreats into deeper cold. Its tiny moon escaped detection for more than a decade because the satellite reflects so little sunlight that it blended into the surrounding darkness despite remaining in view. Haumea scarcely resembles a typical world at all. Measuring nearly 1,100 miles along its longest dimension and only about 620 miles across its narrowest, it spins once every 3.9 hours. That astonishing rotation produces enough centrifugal force, the outward effect created by rapid spinning, to stretch the body into an elongated shape unlike any other known dwarf planet. Haumea also possesses two moons and a ring, placing it among the very small number of minor bodies known to host ring systems. Farther outward, Gong Gong traces one of the more unusual routes through the distant solar system, roughly 750 miles wide. It follows an orbit tilted by about 33 degrees compared with the main planetary plane and travels as far as 101 astronomical units from the Sunday. A small companion accompanies it, adding another example to the remarkable variety of binary relationships beyond Neptune. Quaoar presents a mystery that continues to challenge accepted ideas. About 690 miles across and orbiting near 43 astronomical units. It possesses a ring located well beyond the distance where established models predict such material should gather into a moon. Instead, the particles continue circling independently, suggesting that some important process remains missing from current theories. As our survey reaches farther into the outer darkness, these worlds increasingly appear less like rare exceptions and more like representatives of an enormous, unseen population. Astronomers estimate that dozens of additional dwarf planets likely await discovery within the Kuiper Belt and the scattered disk, hidden only because they remain too distant and too faint for present surveys to reveal. Long before any spacecraft could hope to cross these immense distances again, another explorer began its journey from a very different vantage point. Rather than flying through the Kuiper Belt, it studies the faint light returning from it, from its position beyond Earth's atmosphere. The James Webb Space Telescope has transformed the outer solar system into one of its most rewarding scientific laboratories since beginning operations in 2022. Its greatest strength lies in infrared astronomy, the study of wavelengths longer than visible light, where frozen compounds reveal distinctive chemical signatures. Water ice, carbon dioxide, methane, carbon monoxide, and complex organic materials each absorb and emit infrared light in characteristic ways. Much of that radiation never reaches telescopes on Earth's surface because our atmosphere blocks it before it can arrive. Above the atmosphere, the James Webb Space Telescope observes these wavelengths with remarkable clarity, allowing astronomers to identify substances that previously remained hidden. Those observations quickly rewarded years of expectation. Spectra, detailed measurements showing how matter absorbs different wavelengths of light, confirmed the presence of carbon dioxide ice and carbon monoxide ice on several Kuiper Belt object surfaces. Formation models had long predicted these frozen compounds should survive in the extreme cold beyond Neptune, yet earlier observatories lacked the sensitivity needed for direct confirmation. Now those predictions rest upon observation rather than inference. Eris has provided one of the most intriguing examples. Measurements of its methane ice indicate that the surface may not be as ancient and unchanged as once believed. Instead, portions appear to have been refreshed by material rising from below. Such renewal hints at an interior retaining more heat than expected for a world orbiting so far from the Sunday. The process remains under investigation, yet it suggests that geological activity can persist in places once assumed to have become completely dormant billions of years ago. Pluto has also benefited from this new perspective. By repeatedly examining its delicate atmosphere, across different stages of its elongated orbit. The telescope has detected subtle variations that improve models describing how gases freeze onto the surface and later return to the sky as Pluto's distance from the Sun changes. These observations complement the close inspection made by the National Aeronautics and Space Administration spacecraft that flew past Pluto years earlier, extending that brief encounter into a continuing scientific record. The telescope's discoveries reach well beyond our own solar system. Around distant stars, it has imaged broad debris disks glowing in infrared light, revealing structures that resemble the Kuiper Belt at different stages of development. By comparing those systems with our own, astronomers can place the solar system within a much larger family of planetary architectures. We begin seeing our distant frontier as one example among many rather than an isolated curiosity. As observations continue through the late years of this decade, the pace of discovery has exceeded many early expectations. Each new spectrum, each newly resolved surface, and each comparison with distant planetary systems sharpens our understanding of the frozen outskirts beyond Neptune. Instead of fading farther into mystery, the Kuiper Belt grows steadily more detailed, revealing that even at the edge of the Sun's domain, there is still far more to learn than anyone once imagined. When we finally step back from our own solar system, a broader pattern begins to emerge. The frozen frontier beyond Neptune no longer appears as an isolated curiosity. Instead, it becomes one example within a much larger family of distant structures surrounding other stars. That shift in perspective changes the question itself. Rather than asking whether our solar system possesses a graveyard of unfinished worlds, we begin asking how common such graveyards truly are across the galaxy. Observations collected during the past several decades provide an increasingly consistent answer. Around hundreds of nearby stars, astronomers have detected broad rings of icy debris using infrared observatories and powerful radio telescopes. These structures, known as debris disks, contain countless remnants left behind after planets formed. Although each system differs in age and appearance, their overall architecture strongly resembles the distant population beyond Neptune. Planet formation appears to leave behind these outer reservoirs with remarkable regularity. One of the clearest examples surrounds Fomalhaut, located about 25 light-years from Earth. In 2004, the Hubble Space Telescope captured one of the first sharply resolved images of its bright outer ring. The ring displays an unusually crisp inner boundary, suggesting that an unseen planet continually shapes the debris through gravity. That process closely resembles the way Neptune maintains the structure of the Kuiper Belt, preventing countless smaller bodies from drifting freely across the outer solar system. Even nearer lies Epsilon Eridani, only about 10½ light-years away, making it the fourth closest known star with a planetary system resembling our own. Observations reveal an outer debris disk occupying a region comparable to the Kuiper Belt, along with evidence for a second belt closer to the star. Together, they form one of the strongest structural analogs yet discovered, allowing astronomers to compare another planetary system with our own using remarkably similar features. Vega tells a different story. Although also about 25 light-years from Earth, its surrounding debris disk produces roughly 1,000 times more dust than the Kuiper Belt. Such abundance indicates a much more active environment, where collisions between icy bodies occur far more frequently. The system may simply be younger, preserving the energetic aftermath of planet formation, or it may lack a Neptune-sized planet capable of organizing and stabilizing the distant debris over billions of years. The Atacama Large Millimeter Array has expanded this picture even further. Working at radio wavelengths, the observatory produces detailed maps showing clumps, gaps, and uneven brightness within nearby debris disks. These irregular patterns are difficult to explain through chance alone. Instead, they reveal the gravitational influence of unseen planets disturbing surrounding material, producing signatures strikingly similar to those observed throughout our own outer solar system. As more stars are examined, the conclusion grows steadily stronger. Planetary systems do not merely create planets, they also leave behind immense populations of worlds that never completed that journey. The Kuiper Belt is therefore neither an exception nor an accident. It is one expression of a process unfolding across the galaxy, repeated around countless stars, each surrounded by its own enduring archive of planetary beginnings. A fleeting point of light can sometimes rewrite an entire field of astronomy. In the autumn of 2017, observers scanning the sky detected an object moving through the inner solar system with a path unlike anything recorded before. Its speed was unusually high, and its direction did not match the familiar routes followed by comets or asteroids born around our Sunday. Within days, astronomers realized they were witnessing the first confirmed visitor from another star system. The object received the designation 1I/2017 U1 and the name Oumuamua, a Hawaiian word meaning roughly messenger from afar arriving first. Careful calculations showed that it had entered the solar system from the direction of the constellation Lyra on a hyperbolic trajectory. Hyperbolic simply means an orbit that is not closed. Rather than circling the sun forever, the object arrived from interstellar space, curved briefly through our planetary neighborhood, and then continued outward toward the darkness between the stars. As Oumuamua departed, another surprise emerged. Its motion revealed a slight additional acceleration beyond what gravity alone should have produced. Normally, such behavior is explained by jets of vapor escaping from a comet as sunlight warms frozen material. Yet telescopes detected no glowing coma, no visible tail, and no obvious outgassing. The source of that gentle push remains one of the most closely examined mysteries in recent planetary science. Brightness measurements added another layer to the puzzle. As Oumuamua tumbled through space, the amount of reflected sunlight changed dramatically, suggesting an object with an unusually elongated or flattened form. Some models indicated it may have been nearly 10 times longer than it was wide, while others favored a broad, pancake-like shape. Whatever its exact geometry, it differed substantially from familiar asteroids and comets observed within our own solar system. Among the leading scientific explanations is the possibility that Oumuamua originated as a fragment from a Pluto-like world orbiting another star. Radiation pressure, the tiny force exerted by sunlight itself, may have been enough to account for its unexpected acceleration if the object possessed an unusually thin structure. If that interpretation proves correct, we briefly encountered a remnant from another planetary system's distant reservoir of icy worlds, material cast into interstellar space long before humanity existed. Only 2 years later, another visitor arrived. Borisov displayed none of Oumuamua's strange behavior. Instead, it looked reassuringly familiar. It developed a bright coma, released jets of gas, and behaved like an ordinary comet approaching the Sunday. Spectroscopic observations, measurements that identify chemicals by the light they absorb and emit, showed a composition closely resembling comets from our own outer solar system. The chemistry of frozen bodies, it seemed, extends well beyond our stellar neighborhood. Together, these two travelers carry an extraordinary implication. We detected both soon after developing instruments sensitive enough to notice such faint wanderers. That suggests interstellar space is likely filled with countless fragments wandering between stars, each expelled from distant planetary systems over billions of years. As we watch them pass through our own, you are witnessing evidence that every graveyard of unfinished worlds may eventually send pieces of itself across the galaxy. Imagine stepping outward until every familiar landmark of the solar system has disappeared behind you. Neptune is long gone. The Kuiper Belt has faded into the distance. Even then, you have not reached the true frontier. Beyond that broad ring lies a realm so immense that no telescope has ever seen it directly, yet its presence has become one of the strongest conclusions in planetary science. Astronomers call this distant domain the Oort Cloud. Rather than forming a flattened disk like the planets, it is thought to surround the solar system as a vast sphere extending in every direction. Its inner boundary begins around 2,000 astronomical units from the Sun, while its outer reaches may stretch between 50,000 and 100,000 astronomical units. At its greatest extent, the Sun's gravitational influence reaches nearly 1/4 of the distance to Proxima Centauri, the nearest known star to our own. You might expect such an enormous structure to be visible with the most advanced observatories ever built, yet the opposite is true. No individual object within the Oort cloud has ever been observed resting in its distant home. Even worlds hundreds of miles across would reflect too little sunlight to detect across such staggering distances. The cloud remains invisible, known only through the clues its wandering members leave behind. Those clues arrive as long-period comets. Unlike the shorter period visitors shaped by the Kuiper Belt and scattered disk, these comets require hundreds of thousands or even millions of years to complete a single orbit around the Sunday. Their paths also differ in another important way. They approach from every direction across the sky instead of remaining close to the broad plane occupied by the planets. That pattern carries remarkable significance. A flat source would produce arrivals concentrated along a flat plane. Instead, long-period comets descend from above, below, and every angle in between. Their orbital energies, a measure describing how strongly they remain bound to the Sun, indicate that they begin their journeys from distances matching the predicted location of the Oort cloud. Mathematics, rather than direct imagery, reveals the outline of this hidden sphere. Its frozen residents almost certainly did not originate there. During the solar system's youth, countless icy bodies formed much closer to the Sun within the same protoplanetary disk that produced the planets. Repeated gravitational encounters with Jupiter, Saturn, Uranus, and Neptune gradually flung many of those objects outward. Some escaped forever into interstellar space. Others slowed just enough to remain loosely attached to the Sun, accumulating over hundreds of millions of years into the immense cloud now believed to surround us. Even after billions of years, the Oort cloud does not remain completely undisturbed. A passing star, the gravity of a giant molecular cloud, or the gentle tidal pull exerted by the Milky Way can slightly alter an object's distant orbit. That tiny disturbance may begin an extraordinary inward journey lasting millions of years before a lone comet finally appears above Earth. When you see such a visitor crossing our skies, you are witnessing a messenger released from the farthest known reaches of the Sun's gravitational domain. Look around our world from orbit, and one feature overwhelms every other. Vast blue oceans cover roughly 71% of Earth's surface, shaping weather, climate, and every known ecosystem. Yet that familiar abundance presents a remarkable contradiction. The young Earth formed only one astronomical unit from the Sun, well inside the region where water ice could remain stable during the birth of the solar system. Planetary scientists refer to that dividing boundary as the frost line. It marks the distance beyond which temperatures within the protoplanetary disk allowed water to freeze into solid ice. During the earliest chapter of our solar system, that boundary lay near 3 astronomical units. Inside it, heat from the young sun would have vaporized most icy material before rocky worlds could assemble. If you built Earth only from nearby ingredients, you would expect a planet far drier than the one we know today. That puzzle has guided decades of research. Investigators searched for a chemical signature capable of tracing water back to its birthplace. The key proved to be the deuterium to hydrogen ratio. Deuterium is a heavier form of hydrogen containing an additional particle within its nucleus. Water formed in different regions of the solar system preserves distinct proportions of these two forms of hydrogen, creating a measurable fingerprint that survives for billions of years. Earth's oceans possess a specific deuterium to hydrogen ratio, allowing scientists to compare them with water locked inside asteroids and comets. Some candidates fail the test, others come remarkably close. The comet Hartley 2 provided one of the strongest matches ever measured, demonstrating that at least certain comets originating from the Kuiper Belt share nearly the same chemical signature as Earth's oceans. That discovery strengthened the idea that icy bodies from the distant solar system helped replenish our world's water supply. Another mission revealed a more complicated story. When the European Space Agency guided the Rosetta spacecraft into orbit around Comet 67P Churyumov-Gerasimenko, detailed measurements showed a deuterium to hydrogen ratio very different from Earth's oceans. Rather than weakening the broader theory, this result demonstrated that comets are chemically diverse. Some preserve water closely resembling our own, while others record very different conditions from the early solar system. The evidence increasingly suggests that Earth's oceans accumulated through impacts from several populations of icy and rocky bodies instead of a single source. Water was only part of the cargo. These ancient visitors also carried phosphorus, nitrogen, carbon, and complex organic molecules, ingredients fundamental to the chemistry of living organisms. Each impact delivered another small contribution to a young planet still taking shape, enriching its surface with materials unavailable in sufficient abundance from local rock alone. When we trace those ingredients back across billions of years, the connection becomes unmistakable. The distant reservoir beyond Neptune did more than preserve ancient leftovers from planetary formation. It supplied part of the material that transformed a dry, rocky world into one capable of sustaining oceans, chemistry, and eventually every living creature that has ever looked up at the night sky. Nothing in the outer solar system remains perfectly unchanged. Every orbit, every distant encounter, every faint gravitational pull contributes to an evolution so gradual that no human lifetime could ever perceive it. Yet across billions of years, the Kuiper Belt has been steadily transformed. It is a population in slow decline, preserving countless ancient worlds while continuously surrendering others to the vastness beyond. Since Neptune settled into its present orbit, the belt has been losing members. Some objects experience repeated gravitational encounters that gradually reshape their paths until they are sent inward as comets. Others receive enough energy to escape the sun entirely, beginning solitary journeys through interstellar space. Many more collide with neighboring bodies, breaking apart into smaller fragments that continue the cycle. The pace is almost impossible to notice on ordinary timescales, but over billions of years the losses accumulate. The Kuiper Belt we know today represents only a small fraction of the original population that once surrounded the young Sunday. The central star will eventually undergo an even greater transformation. In approximately 5 billion years, the hydrogen fuel within the Sun's core will become exhausted. Fusion will shift to new layers, causing the outer atmosphere to expand enormously. The Sun will become a red giant, swelling outward until Mercury and Venus disappear within its outer envelope. Whether Earth survives that expansion remains uncertain, though even under the most favorable conditions, it would no longer resemble the world we know. Far beyond those inner planets, the changing Sun will reshape the outer solar system as well. As its brightness increases, the frost line, the distance beyond which water ice remains frozen, will migrate farther from the Sunday. Portions of the inner Kuiper Belt may grow warm enough for surface ice to sublimate, changing directly from solid into gas. Over millions of years, objects that spent nearly the entire history of the solar system frozen in place could begin losing volatile material for the first time. Eventually, the Sun will cast away its outer layers, creating a glowing planetary nebula that expands into surrounding space. At the center will remain only the stellar core, containing roughly one half of the Sun's present mass, compressed into a sphere comparable in size to Earth. This dense remnant, known as a white dwarf, will radiate stored heat while cooling over trillions of years. You might imagine that such a transformation marks the end of the story. Evidence from other stellar systems suggests otherwise. Astronomers studying white dwarfs frequently detect calcium, silicon, iron, magnesium, and other heavy elements within their outer layers. Those materials should sink beneath the visible surface in relatively little time, yet they continue appearing. The simplest explanation is that rocky and icy debris from surviving outer planetary systems keeps falling inward, supplying fresh material long after the parent stars have died. Our own distant reservoir is expected to endure through that same future. Whatever remains of the Kuiper Belt after billions of additional collisions, ejections, and slow erosion will continue circling a cooling white dwarf. Long after the familiar planets have vanished or wandered away, the graveyard itself may still trace the memory of the solar system that once flourished around the Sunday. Progress at the edge of the solar system rarely arrives in dramatic bursts. It advances through patience measured in decades, carried by machines that continue their work long after the teams who launched them have retired. Even today, one spacecraft remains our lone ambassador beyond the Kuiper Belt, still sending faint signals home across an almost unimaginable distance. New Horizons continues its journey at roughly 57 astronomical units from the Sun, transmitting scientific observations while gradually surrendering to time. Its electricity comes from the steady decay of plutonium, a power source that weakens a little more each year. Mission engineers carefully decide which instruments to deactivate, preserving enough energy to keep the spacecraft communicating for as long as possible. If current projections hold, those final transmissions may arrive sometime during the early years of the 2030s, closing a mission that transformed our understanding of the distant solar system. When that day comes, no successor will already be waiting beyond Neptune. At present, no dedicated spacecraft is traveling toward the Kuiper Belt. The next mission to those remote worlds exists largely on drawing boards, scientific studies, and long-term planning. Reaching such extraordinary distances requires commitment across generations, because even the fastest practical missions demand travel times measured in decades. One proposal has captured particular interest among planetary scientists. Instead of racing past a distant object as New Horizons did, A future Kuiper Belt orbiter would slow enough to enter orbit around its destination. Remaining nearby for months or even years would allow continuous mapping of changing surface conditions, internal structure, and possible seasonal activity. Achieving that goal demands propulsion systems capable of reducing enormous speeds after a journey lasting at least 15 to 20 years following launch, making such a mission one of the most ambitious ever attempted. While engineers imagine future spacecraft, new observatories are transforming discovery from Earth. The Vera Rubin Observatory, which began full survey operations during 2025, repeatedly photographs the night sky with extraordinary sensitivity. By comparing image after image, astronomers can identify the slow movement of distant Kuiper Belt objects against seemingly fixed background stars. Tens of thousands of previously unknown bodies are expected to emerge during the observatory's first years of operation, expanding the known population far beyond anything achieved before. Another powerful instrument will add a different perspective. The National Aeronautics and Space Administration's Nancy Grace Roman Space Telescope, planned for launch during 2027, will conduct wide-field infrared surveys that complement Vera Rubin's visible light observations. Together, these observatories will detect fainter and more distant objects than either could discover alone. The European Space Agency is preparing a mission with a different strategy entirely. Comet Interceptor will wait near a gravitational equilibrium point between Earth and the Sun until astronomers discover a dynamically new comet arriving directly from the Oort Cloud. Because such an object has never approached the Sun before, its frozen material preserves conditions dating back to the earliest history of the solar system. For you, this moment arrives at an extraordinary time. The distant frontier has never been better equipped for exploration, and the coming decades promise discoveries that may reshape our understanding of the graveyard beyond Neptune more profoundly than the previous century combined. Words shape the way we understand the universe. Before we continue, it is worth lingering on one of them. Throughout this journey, we have described the distant bodies beyond Neptune as failed planets, yet that familiar phrase carries assumptions borrowed from human experience rather than from nature itself. When you hear the word failure, it often suggests a goal left unfinished or an opportunity somehow lost. The Kuiper Belt tells a different story. None of these frozen worlds made a mistake. None missed a hidden chance to become something greater. Every object simply responded to the environment in which it formed, following the same physical laws that governed every grain of dust, every collision, and every orbit throughout the young solar system. The material available beyond Neptune was spread across an enormous volume of space. Encounters between growing bodies became increasingly uncommon, and the process of accretion, the gradual sticking together of smaller objects into larger ones, slowed dramatically. Before many worlds could gather enough mass to become full-sized planets, time and circumstance closed that chapter. Growth paused, leaving behind countless survivors that still preserve the conditions of those earliest ages. Seen from that perspective, the Kuiper Belt did exactly what physics allowed. It produced dwarf planets, icy binaries, scattered fragments, and comet reservoirs, because those outcomes matched the balance between gravity, distance, and available material. Nothing in that history points toward error. Instead, it reflects remarkable consistency, the predictable consequence of the environment that existed more than 4 billion years ago. As we have discovered along the way, those lingering remnants influence the destiny of the inner solar system in profound ways. They helped shape long periods of bombardment that reshaped planetary surfaces. They supplied water and complex organic molecules, collections of carbon based compounds that can participate in the chemistry leading toward life. They preserved records of the original protoplanetary disk, offering evidence unavailable anywhere closer to the Sunday. Imagine, for a moment, an outer solar system where every icy body successfully merged into a handful of giant planets. The architecture of the planetary system would have changed completely. Gravitational interactions would have followed different paths. The number and timing of comet impacts reaching the inner planets would almost certainly have been altered. Earth's water inventory, and perhaps the broader conditions supporting long term habitability, might have unfolded along a very different course. Several planetary scientists have suggested that the present arrangement of the Kuiper Belt, together with Neptune's stabilizing influence, may represent one ingredient among many that encouraged Earth's enduring stability. Rather than unleashing an endless stream of impacts, this distant reservoir supplied material over immense stretches of time while gradually settling into the balanced structure we observe today. Perhaps the most fitting way to regard this frozen frontier is not as a monument to unrealized worlds, but as a preserved archive of everything the solar system required to become what it is. These distant objects remain exactly where history left them, carrying evidence that the line between success and failure often disappears when viewed through the patient logic of the universe. There are places in the solar system where history has been rewritten countless times. Mountains have risen and vanished, oceans have formed and disappeared. Worlds have melted, fractured, and reshaped themselves through relentless change. Yet, beyond Neptune, another kind of history endured, one preserved with extraordinary fidelity across almost the entire lifetime of the Sunday. When the National Aeronautics and Space Administration spacecraft New Horizons swept past Arrokoth on the first day of 2019, its cameras recorded sunlight reflected from material that had remained largely unchanged for approximately 4,560,000,000 years. That surface already existed before Earth possessed a stable crust, before the giant impact that completed the formation of the Moon had fully settled into history, and before lasting oceans covered our own world. Very few places offer such continuity. Across the inner solar system, intense heat, volcanism, erosion, tectonic activity, and repeated impacts have erased much of the earliest record. Even ancient rocks on Earth preserve only scattered fragments of that distant era. The Kuiper Belt, by contrast, retained objects whose basic structures still reflect the original conditions of the protoplanetary disk, the broad cloud of gas and dust from which every planet eventually emerged. Arrokoth demonstrates this remarkable preservation with unusual clarity. Its gently joined lobes, its reddish surface, and the proportions of its overall shape all provide direct evidence about the local environment where it formed. Rather than reconstructing those conditions through computer models alone, we can compare predictions against an actual surviving object that has carried those characteristics forward through billions of years with remarkably little alteration. Consider the passage of light itself. A beam leaving the sun now requires roughly 7 hours to reach the outer regions of the Kuiper Belt. When those photons finally arrive, they illuminate worlds that have circled their star through nearly every chapter of solar system history without substantial geological renewal. They continue their patient revolutions, while the familiar landscapes of the inner planets experience continual transformation. During that immense interval, Earth's story unfolded almost entirely. The Cambrian explosion filled ancient seas with diverse animal life, dinosaurs dominated continents before disappearing. Mammals spread across changing environments, and eventually human beings learned to observe the heavens with mathematics, telescopes, spacecraft, and careful curiosity. Throughout every one of those chapters, the distant inhabitants of the Kuiper Belt continued along nearly the same paths they followed in the earliest days of planetary formation. Measured against that immense archive, the span of recorded civilization becomes astonishingly brief. Thousands of years, impressive within human history, scarcely register beside billions. Our first written records, our greatest observatories, and our journeys into space all occupy only the final instant of an extraordinarily long narrative. When you look toward the Kuiper Belt, you are not simply looking across distance, you are looking across uninterrupted time. These frozen worlds preserve a physical record that reaches back to the birth of the solar system itself, making this distant frontier the closest thing we possess to an original edition of our cosmic beginnings. Standing at the outer boundary of the Kuiper Belt can create the impression that we have finally reached the end of the solar system. Yet that impression fades almost immediately. The frozen worlds we have explored occupy only the first broad layer of a far larger structure, one whose full extent stretches across distances that challenge ordinary imagination. The Kuiper Belt gradually gives way at roughly 50 astronomical units. Beyond that region, the orderly populations of dwarf planets and icy bodies become increasingly sparse, replaced by the scattered disk. Here, objects follow elongated paths that can carry them more than 100 astronomical units from the Sun before beginning their slow return. Many owe those unusual orbits to ancient encounters with Neptune, whose gravity scattered them outward during the solar system's earliest reshaping. Even farther away lies one of the least understood regions in planetary science. Between roughly 100 and 2,000 astronomical units extends an immense frontier that remains only lightly explored through observation. Sedna, with its extraordinarily distant orbit, briefly enters the inner edge of this realm before traveling far beyond it. Its path hints that this apparent emptiness may conceal additional worlds, waiting beyond the reach of present surveys. Beyond that vast interval, the inner Oort Cloud is believed to begin, followed by the immense outer Oort Cloud. Together they form a nearly spherical population surrounding the solar system in every direction. At distances approaching 50,000 to 100,000 astronomical units, the Sun's gravitational influence becomes remarkably delicate. A passing star, a drifting giant molecular cloud, or even the steady gravitational pull of the Milky Way can gradually redirect frozen bodies that have circled undisturbed for unimaginable spans of time. Human exploration has only begun to approach these distances. Voyager 1, launched in 1977, became the most distant spacecraft ever built. In 2012, it crossed the heliopause, the boundary where the outward flow of charged particles from the Sun gives way to the material-filling interstellar space at approximately 121 astronomical units. Even traveling at roughly 38,000 miles per hour, Voyager 1 will require about 300 years to approach the inner Oort cloud. Reaching the outer limits of that distant reservoir would demand roughly 30,000 years. Those numbers reshape our sense of scale. The planetary orbits, familiar from textbooks, occupy only a tiny central region inside an enormous gravitational domain. Long after the last major planet has disappeared behind us, the Sun still commands countless unseen companions spread across a volume that reaches astonishingly close to the nearest neighboring star. Seen from that perspective, the Kuiper Belt no longer appears to be the edge of anything. Instead, it becomes the opening chapter of the solar system's outer wilderness, the first visible layer surrounding a much greater expanse whose true boundaries remain hidden in darkness, distance, and time. There is another story woven through this distant frontier, one that does not belong to icy worlds alone. It belongs to us. The frozen bodies beyond Neptune reveal the history of the solar system, yet they also reveal something about the curious species that chose to search for them in the first place. Only a few decades ago, the Kuiper Belt had not entered humanity's understanding of the cosmos. 35 years ago, its existence had only begun to emerge from careful observations. 15 years ago, many of its largest known members remained little more than faint, unresolved points of light. A decade ago, Arakoth itself was merely a tiny speck with almost no measurable characteristics. Then, on the first day of 2019, a spacecraft no larger than a piano swept past that ancient world and returned detailed images of an object that had preserved its original form since the birth of the solar system, nearly 4 billion miles from Earth. The pace of that progress deserves as much attention as the discoveries themselves. Within a remarkably brief span of history, human beings learned how to predict planetary motions, build precision instruments, communicate across billions of miles, and guide a robotic explorer through a target smaller than many states after nearly a decade of flight. Every successful calculation represented thousands of earlier ideas refined through patience, observation, and generations of shared knowledge. If you look across history, a familiar pattern begins to appear. Every civilization that studied the night sky eventually found that the universe was larger than expected. Mountains did not mark the edge of the world. The atmosphere did not form a ceiling. The planets were not wandering lights fixed to a crystal sphere. Each discovery replaced certainty with a wider horizon, inviting another careful question rather than a final answer. The Kuiper Belt continues that tradition in a uniquely tangible way. It is distant enough to demand years of planning and travel, yet close enough that determined engineering can still reach it. It occupies a remarkable middle ground where imagination alone is no longer sufficient, but perseverance can transform distant points of light into places with landscapes, histories, and measurable physical properties. Perhaps the most extraordinary detail is how much remained unknown even after New Horizons left Earth. The spacecraft began its journey before the Kuiper Belt had been thoroughly catalogued. Its destination changed as astronomers discovered new candidates. When it finally encountered Arakoth, the observations challenged long-standing ideas about how planetesimals, the small building blocks of planets, assembled during the earliest stages of planetary formation. One carefully planned encounter reshaped theories extending far beyond our own solar system. We did not evolve to think naturally in terms of 4 billion years or billions of miles. Our ancestors learned by watching seasons, rivers, and familiar horizons. Yet, through mathematics, engineering, and relentless curiosity, you and I can now follow machines into regions no human eyes will ever directly see. Reading the oldest surviving pages of the solar system from worlds that waited patiently until someone finally came to ask their story. At this very moment, while you listen, the New Horizons spacecraft continues its outward journey, traveling nearly 5,300,000,000 miles from Earth. Its radio signal moves at the speed of light, yet still needs more than 8 hours to complete the crossing. The stream of information arrives at only about 1,000 bits each second, a remarkably modest pace carrying observations from farther away than any human-made explorer has ever closely studied another world. Its destination is no single object now. Instead, the spacecraft drifts beyond the familiar population of the Kuiper Belt, entering the immense region that stretches toward the inner reaches of the Oort Cloud. No scientific instrument has ever surveyed this territory from within. Every mile carries it deeper into a realm that remains almost entirely unexplored, extending our presence farther than our own senses could ever reach. Out there, sunlight has become astonishingly faint. At this distance, the sun brightens the landscape with only about 1/3000th of the illumination received at Earth's surface. Imagine the gentle glow of a full moon overhead, except suspended within a sky without air, without clouds, and without anything to soften the darkness surrounding it. Even that comparison only hints at the true emptiness beyond the planets. Within that vast expanse, countless frozen worlds continue their patient paths around the Sunday. Nothing rushes them, nothing interrupts them. Their orbits unfold over centuries, millennia, or far longer, guided only by gravity and time. The conditions preserving them have endured since the earliest chapters of the solar system, leaving behind records that no archive built by human hands could ever equal. Arakoth has completed its slow circuit since an era before Earth possessed a permanent moon. Sedna has followed its approximately 11,400-year orbit since long before the first animals appeared in Earth's ancient seas. The cold classical population, preserved in remarkably stable paths, has remained largely unchanged since the protoplanetary disk, the rotating cloud of gas and dust that formed the planets, gradually dispersed. Their histories continued uninterrupted, while continents shifted, oceans changed, and every page of human civilization unfolded in an instant by comparison. As you rest beneath your own evening sky, those distant worlds continue exactly as they always have. They neither celebrate discovery nor acknowledge the spacecraft passing through their neighborhood. They simply remain, carrying within their ancient ice the earliest surviving record of our cosmic beginnings, waiting for careful observation rather than demanding attention. Perhaps that is the lasting lesson of this journey. Across billions of years, the solar system has preserved a memory of its own formation, not in books or monuments, but in worlds that endured because so little disturbed them. Between where you are now and those distant orbits lies an immense separation measured in miles, in light, and in time. Yet, every observation returned across those 8 hours of travel narrows that distance, allowing the oldest surviving pieces of our shared origin to become, little by little, part of our understanding. The journey ends with an unexpected realization. The Kuiper Belt truly is a graveyard, at least by the most faithful scientific description we can give it. It is a vast collection of planetary beginnings that never became full worlds, bodies whose growth paused billions of years ago and whose histories have remained preserved far beyond the orbit of Neptune. They have endured longer than complex life has existed anywhere we know, carrying forward a record written at the birth of the solar system itself. Yet a graveyard can also be an archive. It preserves what would otherwise disappear. Every untouched surface, every ancient layer of ice, every orbit maintained across billions of years adds another page to a story that would have been lost if every fragment had merged into a finished planet. Because these distant objects survived unchanged, they allow us to reconstruct events that no rock on Earth can still remember. Our own world owes more to this distant population than its remoteness first suggests. Water delivered by icy visitors from the outer solar system likely helped fill Earth's basins with oceans. Comets and primitive bodies also carried carbon dioxide, nitrogen, phosphorus, and complex organic molecules the chemical ingredients that expanded the possibilities for life. During the era known as the Late Heavy Bombardment, impacts reshaped the young planets, redistributing material across the inner solar system and influencing environments where increasingly complex chemistry could unfold. Seen from that perspective, these frozen bodies were never discarded pieces of creation. They remained the reservoir from which the successful planets continued to receive essential ingredients. Their existence shaped gravitational pathways, influenced the movement of comets, and preserved the conditions that ultimately allowed one small rocky world to become inhabited. Think again of Pluto, Arrokoth, Eris, and Sedna. Each follows its own ancient path, neither hurried nor altered by the countless events that transformed the inner planets. They were present while Jupiter accumulated its enormous mass. They remained as Neptune settled into its modern orbit. They continued circling while Earth's crust cooled, while oceans gathered, while continents shifted, and while living organisms gradually filled the surface of our planet. Their testimony is written in ice rather than words, waiting for instruments patient enough to read it. Even now, those distant worlds continue their endless circuits around the Sunday. They remain billions of miles away, largely untouched by geological change, preserving physical evidence from an era that predates every mountain, every ocean, and every living creature on Earth. Few places in the solar system have guarded their history with such remarkable fidelity across so much time. The graveyard beyond Neptune is cold. It is remote. Nothing there was truly wasted. Across billions of years, it has protected the earliest surviving chapter of our shared cosmic story. By learning to read that chapter with ever greater care, we discover that the beginning has never vanished. It has been waiting for us all along,